Okay, I think I'll start with the next set of 15 questions. So let's look at this, okay? So in ESR, the contribution of nuclear magnetic moment. What do you mean by ESR? ESR is basically electron spin resonance. So these are the options that are given: exists but neglected, does not exist, exists and considered, has very high value. So you might have heard of nuclear magnetic resonance, right? So nuclear magnetic resonance basically deals with the nucleus. In case of electron spin resonance, ESR basically deals with the spin of the electron. So here, electron spin resonance is also called as electron paramagnetic resonance. And what do you basically mean by paramagnetic? Paramagnetic basically means unpaired electrons. So it's basically a method that is used to study unpaired electrons. That's why it's also called as electron paramagnetic resonance. Now, basically, these are very important because there are very poisonous free radicals that are there. So this electron spin resonance basically helps detect some of these poisonous free radicals that get up in the materials. So any molecular species which is capable of independent existence that contains unpaired electrons in an atomic orbital is called a free radical. Now, EPR is basically, like I said before, it's analogous to nuclear magnetic resonance, but it deals with electron spins that are excited instead of the spins of the atomic nuclei. So in your nuclear magnetic resonance is basically to do with the spins of the atomic nuclei, whereas in the case of electron paramagnetic resonance, it's basically to do with the electron spins that are there. So let's go back to the question. In ESR, the contribution by nuclear magnetic moment, it exists, but it's neglected. So it's option A. Okay, so the thing is that you do have nuclear magnetic moment, but you're not going to be using it in electron spin resonance. So the name itself tells you what the answer is, in fact, if you know what the full form of ESR is. Now, let's look at this. The Frank-Condon principle is based on the principle on the fact that the nuclei are moving with the velocity of light, are having zero mass, are at rest, are neglected. So if you're looking at basically this Frank-Condon principle that you have, let's go here. Okay, so basically it's a rule in spectroscopy and quantum chemistry which explains the intensity of vibronic transitions. So this particular thing, I think you would have learned, this particular principle is usually put in the elective courses, elective AMOP courses. So I don't think this would have been mentioned in the general course as such. So what are these vibronic transitions? It's basically the simultaneous changes in electronic and vibrational energy levels of a molecule due to the absorption or emission of a photon of appropriate energy. So basically you would have seen something like, let's put it this way, you would have seen something like these two vibrational harmonic oscillator potentials and transitions from one level to the other level and so on. Okay, you would have seen something like this. So let's go to the next point. So within the Frank-Condon approximation, the nuclei are considered fixed during the electronic transitions. So this is basically the most important point here. Okay, the nuclei are considered fixed during the electronic transitions. So the electronic transitions can be considered as vertical transitions on the electronic potential energy curves. And these, I think you would have possibly looked at in the third semester of your general AMOP course. So electronic transitions are relatively instantaneous compared with the time scale of nuclear motions. Therefore, if the molecule is to move to a new vibrational level during the electronic transition, this new vibrational level must be instantaneously compatible with the nuclear position and momenta of the vibrational level of the molecule in the originating state of the electron in the originating electronic state. So basically what's this telling is that the initial electronic state that you have, okay, so the initial electronic state that you have and your final electronic state after the transition, okay, when you move from this to this, when there are transitions that occur, basically the nucleus, okay, so let's just draw a nucleus. The nucleus will not move, okay, that's basically what it's summarizing. It will not move. It will not move in position. Its position will not change. Its momenta will not change. So that's what the basic idea behind the Frank-Condon principle. So let's just go back and review the question. Okay, so the Frank-Condon principle states a principle is based on the fact that the nuclei are, what is it? Moving with zero velocity of light, or having zero mass, are at rest, or are neglected. The nucleus does not move is the assumption here. So basically it's option C, are at rest. Okay, so let's move on to the next question. The hyperfine structure and isotope effect are associated with only splitting of the electronic energy levels, only shifting of the electronic energy levels, both shifting and splitting of the electronic energy levels, no change in the energy levels. So the option is basically C, and we'll look into why that is. So anything to do with hyperfine structure has to do with the nucleus. So whenever you hear hyperfine, it's basically something that's to deal with the nucleus. So hyperfine structure is basically small shifts and splitting in the energy levels of atoms, molecules, and ions due to the interaction between the nucleus and the electron clouds. So isotopic effect is basically the effect of the substitution, isotopic substitution on spectroscopy. So that's basically what isotopic effect means. So hyperfine structure is basically to deal with the nucleus, and isotope hyperfine structure is to do with the nucleus, and your isotope effect is basically to deal with what happens when you substitute different types of isotope into the molecule. Okay, so let's look at this. The isotope shift is basically the shift in the various forms of spectroscopy. Spectroscopy is basically to deal with the spectra that you get when you have your absorption and your emission coming up from these, the emission of the absorption of light or the emission of light from the material that you're looking into. So it's used to basically study materials and how their properties are. So it is the shift in various forms of spectroscopy that occur when one nuclear isotope is replaced by another one. And basically isotopic shifts in atomic spectra are minute differences between the electronic energy levels of different isotopes of the same element. So this is the key point here. These are to deal with minute differences between electronic energy levels. So let's go back to the question. Hyperfine structure and isotope effect are associated with what? Is it only splitting of the electronic energy levels? Only shifting of the electronic energy levels? No, it's both shifting as well as splitting of electronic energy levels. That is to do with hyperfine and isotope effect. So yeah, so now let's go into a problem. Now this question is not a very correct question. The options are wrong. The answer key, the revised answer key has wrong. I mean, they said that the options for this are wrong. And I'll even tell you why it is wrong once we get to the problem. So a laser operates at a frequency of 3 × 10⁴ hertz and has a slit width of 10⁻⁻2 meters. The angular spread will be. So these are the different angular spread or angular resolutions that are given to you. Now let's look into what you mean by angular spread or resolution. So basically, it is the ability of an image forming device to distinguish small details of an object. So it is the ability, let's say you're standing far away from the wall and you have 2 points on the wall. The resolution of your eyes would be capability to resolve these 2 points as separate. Okay, so if you look at it from a far off different distance, this is going to be like a blob. But if you look at it closer, it would be 2 separate points. So let's look into the next point. It's basically a major determinant of image resolution. That's why when you always talk about this, when you always talk about image resolution, you do talk about angular resolution or angular spread. So the Rayleigh Criterion shows that the minimum angular spread that can be resolved by an image forming system is limited by diffraction to the ratio of the wavelength of the wave to the aperture width. So what does that mean? So basically any form of angular spread that you would have would be approximately related to the ratio between the wavelength of the incident light divided by your aperture width d. So now, what can be the limitations of the imaging system's resolution? So there are 2 different things that limit the imaging system's resolution. One of them is aberration, okay? And this is something that we can try and better, okay? So geometrical optics is basically the cause of this. So what we can do is we can increase the optical quality of the system, and we can kind of like minimize the effects of aberration. What about the other case? In the other case, you have diffraction, and this is not something that's basically in our hands. It is to do with the wave nature of light, and it is determined by the finite aperture of the optical elements. So it would be determined by the width, aperture width that you have. Okay, so mostly we will be looking into this part, a formula that was derived based on diffraction. So let's look at this. Okay, so the formula for the angular spread, considering diffraction through a circular aperture. So I'm imagining that the aperture is circular because when you look at laser systems, you usually have a circular aperture. So you have theta is equal to 1.22 lambda by d. And where does this parameter 1.22 come from? So you might have heard something called as airy disk. And you basically have fringes that are there. So one of the distance between two of these fringes that you take from the airy disk basically gives you this parameter 1.22. Okay, so let's look into this. So basically theta is the angular resolution, which is given in radians. Lambda is the wavelength of light that's used, and d is basically, okay, so this should have been a little d. D is basically the diameter of the lens's aperture. So let's look into this. So yeah, okay, so now what you need to do is you need to calculate the wavelength of light, because what's given to you in the question is frequency. So let's go back to the question just to recall. Yeah, okay, so what's given to you in the question is the frequency. Okay, so you need to convert that into the wavelength so that you get lambda out. So how do you do that? You take c, you take the speed of light and divide it by the frequency. Okay, so you take the speed of light, you divide it by the frequency, and you get 10 to the power of 4 meters. So if you basically recall the systems, laser systems that we used in our MSc course had something like, let's say, I think this is in the first year of MSc, you would have seen something like 650 nanometers or something like that, a red laser. So look at that wavelength that you had in your red laser and look at this. Okay, so lambda here is about 10 kilometers. It's absolutely ridiculous to have some laser of wavelength of 10 kilometers. Okay, so it should be of the order of some kind of nanometers or angstrom or something like that. So that's why these have wrong options. Okay, they kind of like goofed up on the value of the frequency. That's why you have this issue. Okay, so anyway, let's just proceed with that. So if you do find out the wavelength, it's very easy for you to calculate theta because d is already given to you, the aperture size is already given to you, and you just substitute it and you get something like 10 to the power of 6 radians. Very, very horrible, but just to get the idea of what the question asks for, or if you have the same question repeating later on, this is what it is. None of these options are correct, so this is a wrong question that was given. Okay. So Mausoleus law, this is something that we've already learned in high school pretty much. Okay, so Mausoleus law relates what and what. So wavelength and intensity of X-rays, frequency and applied voltage, frequency and atomic number, wavelength and scattering. Okay, so what does it relate? Mausoleus law is basically an empirical law. It concerns with the characteristic X-rays that are emitted by atoms. The law states that the square root of the frequency of the emitted X-ray is proportional to the atomic number. Okay, so that's what you have here. Nu is basically proportional to Z. Now, what is the exact formula? Because I think there might be questions when you have to deal with K alpha, L alpha lines. So Moseley found that for the spectral lines, this relationship could be approximated by a simple formula, which is called as Mausoleus law. So the frequency is equal to A times Z minus B whole squared. So it's actually it's basically the full formula for the one that you saw previously. So square root of the frequency is proportional to Z. If you do take the square root on both the sides. So Now, nu is basically the frequency of the observed X-ray emission line. A and B are constants that depend on the type of line. So we would have seen that the first orbital gives you a K shell, is named as K, the second is named as L, third is named as M, and so on. So what do you have here? So how do you calculate this? Basically the value of these constants. So what you do is, if you want to calculate it for the K alpha line, this is basically 1 divided by Ni minus Nf. So this 1 squared and 2 squared is basically the initial and the final orbital number. And then you have B is equal to 1 for K alpha lines. The same thing you do with the next line for L alpha. That's the next line of the, here you would have, just a second. So here you would have K, here you would have L. So K is basically referring to, let's say 1, L is basically referring to 2. So you're going from a transition from 1 to 2, and here you're going for a transition from 2 to 3. So these are basically for the L alpha lines. So that has a B value of 7.4. So these are just not related to the question as such. The question stops with the last slide. The answer to the question stops with the last slide, but this is just in case you're asked about finding the frequency exactly for particular K alpha or L alpha lines. Okay, so this is a very simple question if you know how to do addition of angular momenta. So the possible values of total angular momentum J resulting from the addition of two angular momenta, J1 equal to 1 and J2 equal to 2, are 1, 2, 1 and 3, 0, 1, 2, and 1, 2, 3. So basically, if you look at the addition of angular momenta rule, how it goes is it goes from J1 plus J2 to modulus of J1 minus J2. Okay, so what is J1 plus J2? It's 3, 2. What is J1 minus J2 is basically modulus of minus 1, right? So you have 1 here, you have minus 2 here, so that's a modulus of minus 1. So 3, 2, 1. So that's 3, 2, 1 that you have here. So that's option D. So just to go through the details once more. So given two angular momenta corresponding to the angular momentum quantum numbers J1 and J2 respectively, what are the allowed values of the total angular momentum quantum number J? So the answer is basically provided by this theorem called the angular momentum addition theorem, which I just told you about. So the allowed values of the total angular momentum quantum number J, this should have been capital J, given two angular momenta corresponding to the quantum numbers J1 and J2 are J1 plus J2, J1 plus J2 minus 1, and so on. So if you have, let's say from 1, so if J1 is equal to 1 and J2 is equal to 5, you would have that many number increasing. Okay, so it wouldn't just be 3, it would be basically like 6 to 4. So let's say, yeah, so probably I should have reduced that to 2 or something like that. So you would have something over here like 5 plus 2 is 7 and 5 minus 2 is 3. So you have 7, 6, 5, 4, 3. So you've had 5 of them. So based on the values of your two angular momenta that are given to you, you can find out the total angular momenta that are there. Okay, so for each of these values, J takes on the values 2J plus 1. So your M is going to be, you have so many number of M values from J to about minus J. So yeah, so this is what I've initially worked out. So the answer is basically 3, 2, and 1, which is option D. So let's go to the next question. Raman spectra is due to the collision of photon with electron, photon with a molecule, electron with an atom, electron with a photon. So basically, when you look into Raman spectra, you do have a photon and it collides with the material that you have put in for this particular Raman spectroscopy that you have there. So it's basically to deal with photon with a molecule. So that's option B. So coming here, let's just look at this. Okay, so what do you have? You have basically two types of scattering. Rayleigh scattering, where your wavelength of light is same as the particle size, almost same as the particle size. In the case of Raman scattering, you have your wavelength of light less than the particle size. Okay, so Raman scattering results in Raman effects due to inelastic collisions between the photons and the particles or molecules. It involves a change in energy. Such energy changes result in a transition between different vibrational levels of molecules. Okay, so next again is a Raman spectroscopy question. So I hope you got that part right. So the idea is that Raman spectra is due to the collisions of photon with just a second, yeah, photon with a molecule. Okay, so you have laser light that's being incident when you do Raman spectroscopy, and you're hitting it on this material, which is made up of molecules. That's basically how you could look into it very quickly. Okay, so moving to the next one, the energy separation between two consecutive Stokes lines in Raman scattering depend on what? Energy separation between the vibrational levels in the excited state, wavelength of the incident light, energy separation between vibrational levels in the ground state, or intensity of the incident light. So let's look into this. So to look into Raman spectroscopy a little bit more in detail. So the Raman effect consists of the appearance of extra spectral lines near the wavelength of the incident light. So basically, when you do your Raman spectra experiments, you see a peak line, which is basically very, very intense line. And then you have some kind of sublines that are there around here, which are very, very faint. Okay, so there are extra spectral lines that are seen apart from the incident wavelength or the laser light that you use. So Raman lines in the scattered light are weaker than the light at the original wavelength. You actually do see this. So if you look at the intensity versus wave number plot, this is basically intensity, and this is wave number. Okay, so let's just write this as new part. So if you do look into that, you do see a very, very thick, large line, and all the rest are very, very small. So I don't know if you've done this in your BSc, but in my college, they had this experiment. So it was kind of like a repetition when we did it in MSc. Okay, so the Raman shifted lines occur both at longer and shorter wavelengths than the original light. The lines at the shorter wavelengths are usually very weak. I will show this in the next slide. The Raman spectrum is the characteristic of the scattering molecule. The Raman lines occur at frequencies nu plus or minus nu k. Now, nu k is basically a specific property of the material that you use. Okay, so these are the frequencies corresponding to the quanta of the molecular vibrations or rotations of that material. Now, okay, so let's look at this. So basically, this is the very, very high original frequency of light or the laser light that you use to incident onto the material. And these are the anti-Stokes lines and the Stokes lines. So these are basically going to the higher wavelength region, the Stokes lines, and the anti-Stokes lines are going to the lower wavelength region. So this is the increase in frequency. So when you look at this, don't think this is higher frequency. This is the part where you have a higher frequency. So your anti-Stokes lines are in the region of a higher frequency, and the Stokes lines are in the region of a lower frequency. Okay, so let's look at the next line. So if the scattered frequency is lower than the original frequency, the longer wavelength region, the incident light has excited a molecular vibration or rotation, and the optical photon has decreased energy. So this situation is called Stokes scattering, and you have Stokes lines. Okay, so this is basically the lower frequency region that you have, or the longer wavelength. If the frequency of the scattered light is higher than the incident light, shorter wavelength, okay, so this is the wavelength is shorter, frequency is higher, the light has gained energy from the vibrational rotational quanta, and these are the anti-Stokes lines that you see. Okay, so what is the answer to this question? It's basically option A, because the energy separation between the vibrational levels in the excited states are the ones that determine the energy separation between the two consecutive Stokes lines in the Raman scattering. So basically what you're looking at is basically these Stokes lines. When you're looking at the separation between, it's to deal with the excited states. Okay, so the energy difference between the excited states that you have. So now let's look into the next question. Very trivial, actually. You don't really need to know any physics to do this, actually. So the number of photons emitted per second from 1 watt argon ion laser operating at 488 nanometer is approximately what? Okay, so let's look into this. You have different numbers that are given to you. Now, what do you need to calculate? You need to calculate the number of photons. And what is the power of the laser? The power of the laser is 1 watt, or basically the power is basically 1 joule per second. Okay, so you could take the energy to be 1 joule because you want the number of photons that is emitted per second. So the equivalent energy that is emitted per second is 1 joule. Okay, so calculate the energy of 1 photon that is emitted from the argon ion laser. So that's basically easy. E is equal to h nu. Lambda, or the wavelength, is what is given to you. So you do hc divided by lambda and you calculate this and you get so many amounts of joules. The next step that you have to do is you want to find out the number of photons that are emitted per second. So you take the power, which is equal to 1 watt. This is 1 joule per second. So the number of photons is equal to the power divided by the energy of 1 photon. So that's 1 joule per second divided by this energy per photon. So this is for 1 photon. So you can write it as joules per photon here. And then once you do the calculation, you get so many photons per second. So it's about 2.46 into 10 to the power of 18 photons. Let's go back to the question. Yeah, so you have 2.46 into 10 to the power of 18 photons, which is option B. Okay, so let's go to the next question that we have here. The maximum degeneracy of an energy level with principal quantum number n is what? Okay, so you have n squared, you have 2n squared, and you have 2n squared plus 1. Okay, so this question is incomplete. Okay, it's not correctly telling you what the answer, what's principal quantum number you really need to find. So if we look at the hydrogen atom, it is a different, what is the degeneracy that you need to find, not the principal quantum number. What is the maximum degeneracy that you need to find? So I'll be talking about 2 cases here, and I'll try to come to a very, very raw conclusion, but this question is incomplete. Okay, so yeah, so in the hydrogen atom, when you do it, you get a different answer for the degeneracy. Degenerate states, number of degenerate states. And if you do it in a 3-dimensional harmonic oscillator, you get a different answer. But both have a principal quantum number. So this question is not specific as to what's maximum degeneracy you need to find. Okay, so whether it's the hydrogen atom or whether it is the 3-dimensional harmonic oscillator. So let's just look into the hydrogen atom case, which I'll probably discuss in detail. And then I will just state the results for the isotropic 3-dimensional harmonic oscillator. So when you look at the quantum state of hydrogen atom, it's basically specified by 3 quantum numbers. One of them is your n value, which is the principal quantum number, the L value, which is the angular momentum quantum number, and the M, that is basically the Z component of your electron's angular momentum. Now, how many of these states have the same energy is what you basically mean by degeneracy, right? So what's the energy degeneracy of the hydrogen atom in terms of the quantum numbers n, L, and M? For a particular value of L, N, and L, your range of L, so for a particular value of N, your range of L is from 0 to n minus 1. So let's just write that down here. So for a particular value of N, what is the range of L? L is basically from 0 to n minus 1. And each L can have different values. And each L can have different values of M. So the total degeneracy is, you have summation of L is equal to 0 to n minus 1. And then you have the degeneracy in M. Because M, again, has values from minus L to L. So M has values from minus L to L. And the L has values from 0 to n minus 1. So first, when you calculate the degeneracy, you need to look into the degeneracy of M. So if you have from minus L to L, okay, so let's just exclude the 0 from that. So if you exclude the 0 from that, you have 2 L values that are there. And then when you include the 0, you just put plus 1. So that's how you get your 2L plus 1. So let's look into this. Okay, so the degeneracy in M is the number of states with different values of M that have the same value of L. For any particular value of L, you can have M values. Okay, so minus L, minus L plus 1, and so on, till about the actual L value that you have here. And that is about 2L plus 1 values, possible M states for a particular value of L. So you plug in this 2L plus 1 into the degeneracy for M. Let's just look at it again. So here you have N, okay, that's a principal quantum number. If you look at your L values, it can range from 0 to N minus 1, okay. If you look at your M value, it can range from minus L to L. So this basically constitutes 2L plus 1 values, and that's what you substitute here. Okay, so the degeneracy in M is basically 2L plus 1. Now let's look at the next step. So this is basically how you go about it. Once you get the summation, this particular value, you need to start doing the summation. So if you basically look at this, this looks like an arithmetic series, right? So let's put this as L is equal to 1. Okay, L is equal to 0 is what you start with. So the degeneracy value is basically going to be equal to, if you start out with L is equal to 1, you have 2 into 0 plus 1, so that's going to be 1. If you put L is equal to 1, you end up getting your degeneracy value to be equal to 3. So 2 into 1 plus 1, that's 3. Now, once you do that and you find out all the values that you need for the summation, so Sn is basically n divided by 2 into 2a1 plus n minus 1 into d. So a1 is your first term, an minus 1 is the nth term, n is the number of terms that you require. So I would put that as n itself, okay? And then d is the common difference so that I can get the value in terms of n. So once you put this in, so a1 is basically 1. We found that the degeneracy is 1 before. And then you have n minus 1 into d. So when you subtract the value, okay, so the initial value of the degeneracy, d was 1. And then the second value that you found out was 3. So if you do 3 minus 1, you get 2. So d value is basically 2. That's how you have this 2 here. And then you get an n squared. Now, yeah, let's look at this. So this is n squared. Now, if you do include spin degeneracy, okay, you need to double this particular value. So you need, if you do include the spins that you have for each of the individual electrons, if you do include that, then you need to multiply this particular value by 2. Okay, so now that is the case for your hydrogen atom. Now let's look into the isotropic three-dimensional harmonic oscillator. So in case of your isotropic three-dimensional harmonic oscillators, the energy levels are degenerate, and the degree of degeneracy is equal to the number of different sets that you have. So you have nx, ny, and nz because it's three-dimensional. And you add all of them up and you get an n. So basically, once you start doing the calculations, so this particular value would basically mean you have an ny plus nz, which is equal to n minus nx. That's what you substitute here. And you do a plus 1. So I'm not going to go through this in detail because this is not really what we want to do here. I'm just trying to tell you the different things that there are. So this is something that you need to keep in mind. This is what the number of degenerate states are for a three-dimensional harmonic oscillator. So that's n plus 1 into n plus 2 divided by 2. Now, even if you multiply this and you look into it, you do realize that this value is less than the one that you found out earlier. That's your 2n squared, okay? So if you look at the harmonic oscillator that you have, you basically do see that you have your ground state, and then you have a couple of other states, and then you have 5 other states, and so on. So for each principal quantum number, except the one in the ground state, for each of the other levels, you do find degenerate energy levels. So that's why they say only the ground state is non-degenerate. All the rest of the states, all the rest of the higher states that you have are always degenerate. You always have company along with the higher values that you have. So all the other excited states that you have. Okay, so let's go back to the question because I think I talked a lot about the details here. Okay, so the maximum degeneracy of an energy level with principal quantum number n is what? You have n squared, 2n plus 1, 2n squared, and you have 2n squared plus 1. So you do realize that the maximum degeneracy for either, if you include the case of the three-dimensional isotropic harmonic oscillator, or if you include the case of uh, the hydrogen atom, you do find that you have 2n squared, which is the maximum value. Okay, so if you have confusions about how is this the maximum value in comparison to your three-dimensional harmonic oscillator, which had n plus 1 into n plus 2 divided by 2, multiply this and see out. Okay, so you multiply this and check it around with this, you do see that this is higher. Okay, and they're asking for the maximum degeneracy. So irrespective of the system, if you compare both the systems, you do not find this value anywhere here. So you can choose this particular value, option C. So this is an incomplete question, but the option is given as C. You could have challenged it. I think probably nobody challenged it that year. Okay, so let's go to the next question. Okay, so basically what this is to deal with is, let's look at this. So a two-dimensional lattice has the basis vectors 2i and I plus 2j. The basis vectors of the reciprocal lattice are pi I plus pi by 2j and all of these different options with pi and without pi and minus and plus and all that. Yeah, okay. So given A is equal to 2i cap and B is equal to I cap plus 2j cap, what do you have here? You basically have your basis vectors that are given to you. So these two are your basis vectors. Basis vectors. In what space is it? This is in the direct space or lattice. This is in the direct lattice. What you want to do is you want to go from the direct lattice to the reciprocal lattice. And how do you do that? Basically, this is the Fourier transform. The reciprocal lattice is the Fourier transform of the direct lattice. Okay, so that's the whole idea behind this. Now let's go to the next line. So let us assume that the third translational vector C of the given lattice lies along the z-axis and it has a unit magnitude, that is C vector is equal to k cap. Okay, so why is that? Because in your question you had a two-dimensional lattice. Okay, so you're basically looking at the x axis and the y axis here. So in order to calculate the volume, what you need to do is first you need to assume that the C vector that is along the into the plane of paper or out of the plane of paper is basically the K vector. Okay, so now what you do is you need to calculate the volume of the unit cell. How do you do that? You need to calculate the scalar triple product. Okay, triple product. Okay, so once you calculate the scalar triple product, which is A dot B cross C, so you have 2i cap, which is the A vector, and this is this B vector that you have, which is given to you in the question, I cap plus 2j cap, and you cross it with the K cap. So first, what you should do is you should always do the cross part first. Okay, so this bracket has to be there, and then you have a dot. So you do this part first, and then you do this part. So let's do this. I cap crossed with K cap is basically minus J cap. Okay, and J cap crossed with K cap is basically I cap. So here you have a minus J cap and you have a 2 associated with this I cap. So you have a 2 I cap there. And then once you start doing I dot, let's say J, you get a 0. And here when you do I dot I, you end up getting a 4 once you multiply it. So you have a 0 plus 2, which is equal to 4. Okay. So now let's go to the next step that you have. Now, these formulas you really need to remember. Also, when you're looking into chemistry, I don't think these 2 pi's are there. In physics textbooks, you do see the 2 pi here. So what are the basis vectors for the reciprocal lattice? So that basis vector is basically denoted by A star and B star that you have here. Okay, so that's basically B cross C divided by the volume. Okay, so that's basically the scalar triple product. If you wanted to find out for A, you do a B cross C. If you want to find out for B, you do a C cross A. It has to be cyclic. Okay, so this B cross C divided by the volume of the unit cell, that's A dot B cross C. And this is C cross A divided by the volume of the unit cell, which is A dot B cross C. Okay. So let's look into how to do them. Okay, so you know that your B cross C, what did you get? This is the value of B that was given to you in the question. So that's I cap plus 2 J cap crossed with your K cap, which you assumed. Your C was assumed to be K cap. And then what is the volume of the unit cell that you had? You had 4 that you calculated earlier. So here you have a 2 pi factor that's there. Once you start doing this, you have an I crossed with a K, that's a minus J, 2J crossed with K, that's a 2I. And once you simplify this, you end up getting pi I cap minus pi by 2 J cap. Similarly, for the B star, the reciprocal lattice basis vector B, you have 2 pi C cross A divided by the volume that was calculated earlier to be 4. You have 2 pi by 4 into K cap crossed with 2I cap. So K cross I is basically J. So you have pi J. So let's look back at the question. Two-dimensional lattices, the two-dimensional lattice has the basis vectors 2I and I plus 2J. The basis vectors of the reciprocal lattice are, you have option D here, which is pi I plus pi by 2J and pi J. So this is how it was given in the question. You're supposed to, these are actually unit vectors, okay? So just a second. Yeah, these are actually unit vectors that you see here. Okay, this is how your question was framed in the question paper. So I just took it as such. All of these are unit vectors. Okay, so let's move on to the next question. Okay, so this one has a little bit of a work that you should do on your own. I will just tell you how to do it. So which one of the following pairs of crystal structures can have the same packing fraction of 0.74? Packing fraction is something that you've started working on since 12th standard. So yeah, I'll just tell you how to, I'll just recap how to do it, and then I want you to do it for 2 of these crystal structures. So BCC is basically base of body-centered cubic, and BCT is basically body-centered tetragonal. Okay, so this structure is quite complicated. Okay, this BCT is complicated. Also, for calculating your HCP, hexagonal close packing, is also complicated. So I want you to look into these structures, BCT and HCP, and calculate the packing fraction for those particular things. But I will tell you how to do it quickly here. Okay, so these are the values that you have. So for body-centered cubic, you have a packing fraction of 0.68. For face-centered cubic, you have a packing fraction of 0.74. Closed packed hexagonal, or your hexagonal closed packing, you have 0.74. Diamond structure, that's your body-centered tetragonal, you have a 0.74. Okay, so with that particular table, you know that the option for this question is basically option D. Both face-centered cubic and hexagonal closed packing have a packing fraction of 0.74. Now let's look into this. So the atomic packing factor that you have, or the packing efficiency or packing fraction, what do you basically look into? So it is the amount of, it is the number of atoms that you have in this particular crystal structure that's there. Okay, so it is a fraction of the volume of the crystal structure that is occupied by the constituent particles. So how do you calculate that? You basically have to look into the volumes of the atoms in the unit cell divided by the volume of the unit cell itself. So let's look at this. Okay, so for simple cubic packing, what you basically have is, I'm not going to try and draw a 3-dimensional image. Okay, so this is how you would have it all around. Okay, so this is basically 1/8 of your atom is here. Okay, so if you have that at 8 of the corners, you basically have 1 atom as the contribution of the entire unit cell. So here what you have is, this is the radius of the atom. This is also the radius of the atom. You basically have 2r equal to the side of the unit cell, which is A. Okay, so 2r is equal to A. And what do you basically do? You want to find out, let's just move on to the next point. Okay, so here basically you have the number of atoms in the unit cell into the volume of the atom divided by the volume of the unit cell. So since the unit cell is a cube, you basically have A cube, but we earlier found out that A is equal to 2r. So you basically have 2r whole cube, and 1 is basically the number of atoms in the unit cell that you found out, because 1/8 is the contribution from each of the corners of the unit cell You have to multiply that 8 times, so you have 1 atom inside the unit cell. So 1 into 4 by 3 pi r cubed, which is the volume of the atom itself. And then once you substitute this and simplify it, you end up getting a packing fraction of 0.52 or so. But this is very simple for a simple cubic packing. Now let's just look into, I will do the FCC one. So the FCC one basically is a face-centered cubic unit cell. So that means you have something like this. Okay, so you have half of the atom inside like this and half outside. Okay, so here also you have that, here also you have that. On top of that, you have one on top like this. Okay, so let me just color that. And one at the bottom like this. Okay, so all of these are basically halves. And not just that, you also have the 1/8 contribution from each of the corners, right? So let me just change the color to blue or something. Yeah. So basically you have 1/8 contribution from each of the corners that you have. That is also there. So basically, let's just go in step by step. So corners basically give you about a 1, and all the others give you about 3. So you basically have 4 atoms in one unit cell. Okay, so how do we calculate this 2r root of root of 2? So how do we calculate that? Basically, you have one atom here. Okay, I'm just drawing the front face, and you have a contribution from here and here. So what is the value of the diagonal of a square? You have root 2r or root 2a. And each of this is r, this is an r, this is an r, this is an r. So that's equal to 4r. And how do you calculate the a value? Basically 4r divided by root 2, and that should give you 2 root 2r. So that's what you have here. So you do the same thing. You calculate the number of atoms in the cell. So that's 4. We looked into that earlier. Then you have volume of the atom. That's 4 by 3 pi r cubed. And then you have a volume of the unit cell, which is this whole cubed. So once you start calculating that, you get something like 0.74, which is what you get for your face-centered cubic unit cell. Now what I want you to do is, like I told you before, there are 2 more structures that are there. One is the hexagonal closed packing, which also has a 0.74 packing fraction. And the other one that you have is a body-centered tetragonal, which also has a 0.74 packing fraction, which I mentioned in the table before. So the thing is that you can't really sit down and calculate this during the exam. So basically mug up the table, but actually work it out at least once. So work it out once and just remember the values that you have there. Okay, so let's go to the next slide. Okay, so ionic solids are, this is very trivial. This is possibly something that you learned in your 10th. Ionic solids are soft and brittle, hard and brittle, malleable and ductile, malleable, hard and brittle. So ionic solids, let's just review all of that. 10 standard basic chemistry that we had. Okay, so ionic solids are basically a result of a metal atom donating its outer shell electron to a non-metal atom. Okay, so you have a metal atom, you have a non-metal atom. So now what do? The metal becomes positively charged. The metal atom, once it loses that, basically becomes positively charged because you have an extra proton in the nucleus. So it becomes a cation, and the non-metal becomes an anion. And basically these are salts that are usually, when you look at ionic compounds, most of them are salts. And these are also, they also have a regular pattern, so they are also called as crystalline. Now, ionic solids are very hard and brittle. That is option B. And why is it hard? Hard is because it has strong bonds, because ionic bonds are very strong. And 2, why is it brittle? So basically what happens is when you have, let's say, 2 cations coming together, okay, or 2 anions coming together, there is a very strong repulsion. So let's say, yeah, so let's say you have some region, you have these 2 cations that are coming together. So there is a very strong repulsion between these 2 cations. Same for the case of anions. And because of that, they become very brittle. Okay, so they distort the whole structure that is there. Okay, when they move close to each other, and because of that, it shatters the crystal, and that's why they're very, very brittle. Okay, so let's move to the second last question. Now, in case of instability of a cubic crystal, what we can see, okay, so we've got a couple of parameters that are being shown. This requires a little bit more discussion in depth. So here we have a C44, which is less than 0, C44, which is greater than 0, C11 greater than C12, and C11 equal to C12. So there's something called the Bohr's instability parameters. Okay, so this is something that you will look into this form, or the tensor form of the Hooke's law, something that you will see in your fourth semester. Okay, so let's look into this a bit detail. So the tensor form of the Hooke's law for the stress-strain relationship in a crystal is sigma is equal to C epsilon. Okay, so sigma is basically the strain, epsilon is the stress, and C is the stiffness tensor that you have. Okay, so this is how it looks. Okay, once you do your Kronecker delta product, I'm not going to go in too detail into it. I'm just showing you how it looks like. So this is how your C looks like. So the C11, C12 are basically each entry in the stiffness tensor. Okay, so C11, C12. And basically what you saw in this question is they are specifically asking you for a cubic crystal, which is the simplest one that is there. Okay, so let's go to the next slide. Now, for a crystalline system, what happens is, due to the cubic symmetry, the stiffness tensor reduces to a couple of few parameters. Just 3 parameters are there here now: C11, C12, and C44. Okay, 3 parameters are there in the stiffness tensor. So yeah, so the cubic crystal system has the simplest form of elastic metrics with only 3 independent constants: C11, C12, and C44. Now, okay, so who actually started off looking into this? So the conditions of mechanical stability of unstressed crystalline structures, like this cubic crystal that we were talking about, this was done by Max Born. And his work basically gives the generic requirements that you require for elastic stability of crystal lattices, and gives simplified equivalence for the generic conditions for some high symmetry classical, for some high symmetry crystals classes. Okay, so here in this particular question, we are looking into a very specific form for the cubic crystals. Okay, so the condition of stability reduced to this form. So C11 minus C12 is greater than 0. C11 plus 2C12 is greater than 0. C44 is greater than 0. So let me just write that down here. C11 minus C12 is greater than 0. C11 plus 2C12 is greater than 0, and C44 is greater than 0. So if you go and look back at your question, okay, so the case of instability of a cubic crystal, C44 is greater than 0. Okay, so they're looking for instability. These are called the stability conditions. So these are the formula that tell you that they are stable. So they're looking at instability. So that means this is there in the stability condition. Which one? The C44 greater than 0. This means stable. This means stable. This means unstable, and this also means unstable. So that's why I wrote. That's why in the next slide, if you look at the option D as well as option A. Okay, so it's not just one of the options, it's both option D as well as option A. Now to go in depth a little bit more, okay, to go in depth a little bit more and not just talk about the conditions of stability, the above equations for the cubic crystal are well known and are often called as Born stability criteria. Okay, so there are very generic forms as well as specific forms for each crystal system. So there are very long, huge papers that are there on finding the Born stability criteria for each different type of Bravais lattices that you have. Okay, so one important thing to note is that the C matrix is definite positive. Also, all eigenvalues of C are positive. That's very important to note. So in case you see C44 less than 0, that means that it is an instability that you see. Okay, instability. So that's the option A that you saw earlier. Okay, so these are necessary insufficient conditions. Now, just to let's say, just to pick around this whole thing a little bit. Let's go back. So you had seen that C11 minus C12 is greater than 0, and C11 plus 2 C12 is greater than 0. So what you do now is you add these two equations up, okay, inequalities up. How do you do that? You basically have 2C, okay, so let me just multiply this with a 2. So 2C11 minus 2C12 is greater than 0. And you see that you have C11 plus 2C12 is greater than 0. So if you add both of these up, you get 3C11 is greater than 0. Okay, because this is minus 2 and this is plus 2, it gets cancelled. So basically what you have is a C11 greater than 0. So if you have these two conditions, this condition that C11 is greater than 0 is automatically implied, and that's what I've stated here in the next couple of things. So here we merely know that the first two conditions imply that C11 is greater than 0. So it needs to be not noted as an extra condition, but it is sometimes done as such in some textbooks. Okay. So also the first condition that you saw, C11 minus C12 is greater than 0, can be written this way also. That's also fine. Okay, so let's come to the last question. Match the material properties list 1 with units list 2. This should have been 2, not 11. Okay, so list 1 is basically specific heat, carrier mobility, thermal conductivity, thermoelectric power, and these are the different units that you have for each of these things. So I'll just go through each of these parameters and kind of like a little explore into the definitions of each of these a bit. So what I know from my memory is that I know that specific heat is basically joules per mole per Kelvin. It's something that I remember from my PU. So for me, 1 is basically B. Okay, so this is a quick way to do it. So 1 is basically B is something that I know. So these two options are ruled out. Okay, so A and D are ruled out. Now carrier mobility is also something that I know. Okay, so it's basically I since I solved problems on this, I know that it's this option. Okay, so it's option. So basically 2 is associated with this, so even this can be ruled out. So that's how these problems have to be looked into. You don't have to like keep checking for each. You don't have to like keep looking into each of the parameters that are there. Okay, so somewhere you would be able to save time. Now, if you do not know any of this, so let's just go into the definitions in a little bit detail. So specific heat is basically the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So what you have here is this is what you want. You want the specific heat capacity. So C is equal to Q by M delta T. So Q is what? Q is in joules. M here you usually take in moles. Okay, not in grams. You usually take in moles, and T is in Kelvin. So you basically have joules per mole per Kelvin. So that's the first thing that I talked about. Let's move on to the next definition. So carrier mobility. What do you mean by mobility? It's basically the measure of ease of a charge carrier drift. So it basically tells you how quickly a charge can move through the material. Now, okay, so basically what you have here is when you have an electric field that's across a material, the electrons gain a net velocity in the direction of the field called the drift velocity. So this is probably some kind of a derivation that you must have done. Yeah, you would have said, okay, fine, you kind of like put these charges here and you put an electric field here, E, and then you would have calculated the drift velocity. This is a definition that's there in the PU textbook. So yeah, so this is how your drift velocity is defined. But when you're looking at the carrier mobility, you're looking at drift velocity per unit electric field. Okay, so mobility is basically drift velocity per unit electric field. So that's basically the shortest definition of mobility that I can give you right now. So yeah, here you have mu n comma p. So this mobility basically applies to both electrons as well as holes. It's not just electrons that are there, but holes as well. So that for that you would write it as mu n, this you would write it as mu p. Okay, so let's go to the next one. Thermal conductivity, that was the third thing that was there in the question. So K is equal to QD divided by A delta T. So once you start substituting the values over here, you would try to, you could try to get the value of thermal conductivity. So you would have Q D divided by A delta T. So you have joules, you have D, which is basically the distance, that would be in M. You have an area, so that would be meter squared, and then you have temperature difference, that's Kelvin inverse. So it would have something like joules, meter minus 1, K minus 1. Okay, so if it's in watts, what you would have is watt. Basically, you need to divide and multiply it by an S. So watt second meter minus 1 Kelvin minus 1. So that's how you could just, directly find out the values of the units. Just remember the formula and substitute the values of the units. Okay, so what do you mean by thermal conductivity of a material? It's measured of the ability to conduct heat. It is the rate at which heat is transferred by a conductor through the unit cross-sectional area of the material. That's why you divide it by an A. Okay, that's why you're calling it unit cross-section when a temperature gradient exists perpendicular to the area. So now, before I talk about thermoelectric power, I want to talk about something called Seebeck effect. So Seebeck effect is basically the buildup of an electrical potential across the temperature gradient. Okay, so this is basically how the thermocouple works. Okay, so you would have different temperatures, let's say a hot region. You would have a hot region and you would have a cold region. And if you put a conductor across that, you would see that you would see that there is a potential difference that is being developed here, an electrical potential difference that's being developed. Okay, so coming to thermoelectric power. Thermoelectric power is basically your Seebeck coefficient. It's also called as thermopower or thermoelectric power or thermoelectric sensitivity and so on. So it is a measure of the magnitude of an induced thermoelectric voltage in response to a temperature difference across that material as induced by Seebeck effect. Okay, so the SI unit is basically volts per Kelvin. Okay, but the more easy unit is basically easy way to talk about this is terms of microvolts per Kelvin. Yeah, so the Seebeck coefficient is the voltage buildup when the small temperature gradient is applied to a material and when the material has come to a steady state where the current density is 0 everywhere. If your temperature difference, delta T, between the two ends of the material is small, then this is how you can define your Seebeck coefficient. S is equal to minus delta V divided by delta T. So basically this would be volt per Kelvin. That's what you would have here. Okay, so that's it for today. This is the last slide for this lecture.